Hello, dreamers. Welcome back to Hafee Sleep, your cozy corner of the universe where restless minds find stillness and weary souls find rest. Whether you're curled up under blankets at midnight, unwinding after a long day, or just needing a moment of calm in a busy world, I'm so glad you're here. You know, one of my favorite things about this channel is knowing we're all drifting off together, yet miles apart. Maybe you're watching from a rainy city in Norway, a sunny balcony in Sydney, or a quiet bedroom in Toronto. Wherever you are right now, take a deep breath with me. If these moments of peace matter to you, do me a tiny kindness. Tap subscribe and the little bell so Hafee Sleep can always find you when you need it most. Give this video a thumb up. It tells the stars and the algorithm that calm is contagious. And most importantly, drop a comment below. Tell me your location and time of the day. I love to see where these sleepy science stories are drifting off to. Let's build a constellation of calm together. Seeing where you are and when you watch helps me create the perfect sleep sanctuary just for you. Now, let your shoulders soften, your thoughts unwind, and let's drift gently into tonight's journey. Close your eyes if you wish, or just let your gaze grow soft. I'll be right here with you as we enter the quantum valley. You're bouncing a ball. Simple, right? You throw it down, it smacks the pavement with a satisfying thwack, springs back up. You catch it. Predictable, reliable, comforting. That, my friend, is the world according to classical physics. It's the physics of our everyday lives. The arc of a baseball, the rumble of thunder after lightning, the steam rising from your coffee cup, the planets dutifully orbiting the sun. It's the grand, sweeping stage play of the universe, where everything has its place, its path. And if you know the starting conditions well enough, you can predict exactly where that ball will land, where Mars will be in 6 months, or how fast that train needs to brake to stop at the station. It's the physics built by giants like Sir Isaac Newton and his famous Apple gravity moment, and James Clerk Maxwell, who brilliantly corralled electricity, magnetism, and light into one elegant set of equations. Classical physics is powerful, intuitive, and it works magnificently well, right up until you try to look at the universe really, really closely. Now imagine trying to watch that bouncing ball, but instead of a nice solid rubber sphere, it's shrunk down, way down to the size of, say, an electron. You focus your super powerful microscope, and something utterly bizarre happens. The ball doesn't follow a neat, predictable arc anymore. One moment it seems to be here, the next instant it seems to be over there, without visibly traveling the space in between. Sometimes it looks like a tiny, solid particle, a speck of dust. Other times it behaves like a shimmering wave, spreading out and interfering with itself, like ripples on a pond. Trying to pin down its exact position and speed at the same time feels like trying to grab smoke. And if you try to see which path it actually took to get from your hand to the ground, the very act of looking seems to change what it was doing. Welcome to the utterly fascinating, deeply weird, and profoundly important realm of quantum physics. This is the physics of the incredibly small. Atoms, electrons, photons of light, the fundamental building blocks of everything. It's a world governed by probabilities, uncertainties, and phenomena that defy our everyday common sense, built by pioneers like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. Yes, that Schrödinger of the infamous cat. So, what's the real difference? It's not just size, though that's a big clue. It's a fundamental shift in how reality itself seems to operate. classical physics is like a grand, deterministic clockwork universe. Quantum physics is like, well, it's like the universe playing a game of dice, where the dice are made of probability waves, and the rules change depending on whether you're watching. Let's peel back the layers and explore this magnificent, mind-bending tango between the world we see and the world that is. Now let me explain the classic physics first. Imagine the universe as a vast, intricate machine. Every gear, every lever, every moving part follows precise, knowable rules. If you could know the position and momentum, that's mass times velocity, of every single particle in the universe at one instant, and you knew all the forces acting upon them, gravity, electromagnetism, etc. Classical physics promises you could calculate exactly where every single one of those particles would be, and what they'd be doing for all future time. It's total predictability, determinism. Cause and effect rule supreme. Drop that apple, gravity causes it to fall, accelerating at a precise, calculable rate, 9.8 meters per second squared, near Earth's surface. Smash 2 billiard balls, you can calculate exactly where they'll go and how fast, based on their masses, speeds, and the angle of impact. Shoot a cannonball, its path is a beautiful, predictable parabola. Heat up some water, the molecules jiggle faster, predictably transferring that energy, eventually turning liquid to gas. Light, a wave rippling through an invisible medium called the ether, behaving exactly like waves on water, reflecting, refracting, interfering. Classical physics breaks down neatly into powerful branches: Newtonian mechanics, the rules of motion and gravity. FMA, force equals mass times acceleration, is its cornerstone. It explains orbits, falling objects, car crashes, and the spin of a gyroscope. It deals with big things moving at speeds much slower than light. Classical electromagnetism. Maxwell's magnificent equations unify electricity and magnetism and reveal that light itself is an electromagnetic wave. It explains motors, generators, radios, rainbows, and why a fridge magnet sticks. Classical thermodynamics, the science of heat, temperature, and energy transfer. It tells us why heat flows from hot to cold, why engines can't be 100% efficient, and gives us concepts like entropy, a measure of disorder, always increasing in closed systems. Classical physics is concrete, visualizable, and deeply satisfying. It powered the Industrial Revolution and took us to the moon. It feels right. You throw the ball, it follows the path. The comfortable, predictable world of classical physics. It felt so complete, so finished. Think of it like a magnificent, ornate grandfather clock, its brass weights gleaming, its pendulum swinging with metronomic perfection, its chimes echoing with reassuring certainty. Generations of brilliant minds, Newton, Maxwell, Boltzmann, Carnot, had seemingly wound it up and set it ticking for eternity. Planets orbited, steam engines chugged, light waves rippled, heat flowed predictably. It was a universe governed by elegant, knowable rules. If you knew the starting push, you could calculate the path forever. Cause and effect were kings. But science, by its very nature, is restless. It doesn't just admire the clock. It wants to open the back panel, peek at the gears, understand exactly how it all meshes together. And towards the end of that confident 19th century, physicists started wielding new, more powerful tools, not screwdrivers, but mathematics and ingenious experiments to peer deeper than ever before. They aimed their gaze not at billiard balls and cannonballs, but at the insides of atoms and the very nature of light itself. It was like taking a magnifying glass to the clock's most delicate, miniature components, And that's when the first, faint, unsettling squeaks began. Tiny at first, easily dismissed perhaps as imperfections in the tools or calculations, but they persisted. They grew louder. They weren't squeaks. They were the sound of fundamental gears, grinding, threatening to jam the entire magnificent mechanism. Let's step into that lab, smelling faintly of ozone and oiled brass. Picture the scene. One group of physicists is intensely studying the light given off by hot objects. This is called blackbody radiation. Think about it. Your old-fashioned incandescent light bulb filament, glowing yellow-white, or a piece of iron heating up in a forge, shifting from dull red to orange, then yellow, and if hot enough, towards white and even blue. It's a common, everyday phenomenon. Classical physics, armed with its triumphant understanding of thermodynamics, heat, and Maxwell's brilliant wave theory of light, felt supremely confident it could explain exactly how much energy is emitted at each and every color, every frequency of that glowing light. They had the equations, derived from solid, well-tested principles, but the calculations, they led somewhere absurd, utterly, catastrophically wrong. The equations predicted that as you looked at higher and higher frequencies of light, way beyond blue, into the ultraviolet region and beyond, the energy emitted by a hot object should skyrocket. Not just increase, mind you, but shoot up towards infinity. Imagine your toaster, instead of gently warming your bread, suddenly blasting out an intense, searing beam of ultraviolet and X-ray radiation, vaporizing not just your breakfast, but your entire kitchen, your house, and probably the neighborhood. It was ludicrous. It violated everything they knew about energy conservation. Experiments clearly showed this wasn't happening. Hot objects emitted most of their energy in the visible or infrared, depending on temperature, and the energy output dropped dramatically at those high ultraviolet frequencies. This glaring mismatch between theory and reality wasn't just a small error, it was a full-blown crisis. They called it, quite dramatically, the ultraviolet catastrophe. It was as if the clockwork, when asked to calculate the chime for midnight, instead predicted the clock would explode with the force of a supernova. Clearly, the classical understanding of how matter emits light was deeply, fundamentally flawed, especially when dealing with the high energies associated with those high frequencies. The gears were binding. Meanwhile, in another corner of the physics world, a different, equally puzzling experiment was causing headaches. The photoelectric effect. Shine a light onto a clean metal surface, like zinc or cesium, and sometimes electrons get kicked right out of the metal. You can measure these ejected electrons, see their energy. Classical physics, again leaning heavily on the well-established fact that light is a wave, reasoned like this. Light waves carry energy. The brighter the light, the more intense the beam, the more energy it delivers to the metal surface per second. Therefore, brighter light should kick out electrons with more energy. It seemed straightforward, like ocean waves hitting the shore. Bigger waves, more intense light, should knock pebbles, electrons, further up the beach, give them more kinetic energy. But reality, once again, stubbornly refused to cooperate. Experimenters like Heinrich Hertz, who incidentally first observed the effect, and Philip Lenard found something deeply weird. It wasn't the brightness that determined the energy of the ejected electrons. It was the color, the frequency of the light. Imagine you're trying to unlock a very stubborn door. You have a huge bunch of keys, your light source. Classical theory says that shaking the entire keychain really hard, high intensity, brightness, should eventually jiggle the lock open, and the harder you shake, the faster the key should fly out once it turns, higher electron energy. But what actually happened was stranger. If you used a red key, low-frequency red light, no matter how violently you shook the keychain, no matter how blindingly bright you made the red light, the lock wouldn't budge. Not a single electron popped out. But then you try a blue key, higher frequency blue light. Even if you barely jiggle the keychain, even if the blue light is incredibly dim, just a faint glow, click. The lock opens and an electron flies out. And crucially, the energy of that ejected electron depended only on the color's frequency of the light, not its intensity. Brighter blue light kicked out more electrons, but each one had the same energy as those kicked out by dim blue light. Red light, no matter how bright, did nothing. This was utterly baffling for the wave model. Why would the color matter so much? Why couldn't brute force, intensity, overcome the problem? It was like the metal surface demanded a specific, precise key shape, frequency, to unlock the electron, and simply bashing harder with the wrong key was useless. This experimental fact sat like a burr under the saddle of classical physics, an irritating puzzle they couldn't solve with their wave-only view of light. The clock seemed to be telling time perfectly for some things, but for this specific task, its hands just spun wildly. And then, the most profound problem of all, lurking right at the heart of matter itself: atomic stability. By the early 1900s, thanks largely to Ernest Rutherford's brilliant experiments where he shot alpha particles at thin gold foil, physicists had a new picture of the atom. Gone was the old plum pudding model, a diffuse positive cloud with electrons stuck in it. Instead, Rutherford revealed the atom as mostly empty space, with a tiny, incredibly dense, positively charged nucleus at its center, like the sun, and much lighter, negatively charged electrons orbiting around it, like planets. It was a beautiful, solar system-like model, and classical physics promptly declared it impossible. Why? Because of James Clerk Maxwell's own laws of electromagnetism, laws that were pillars of the classical edifice. Here's the deadly flaw: an electron orbiting the nucleus is constantly changing direction. It's moving in a curve, accelerating towards the center. And Maxwell's equations state, unequivocally, that an accelerating electric charge must radiate away energy in the form of electromagnetic waves, light. Think of it like a satellite in orbit. If it loses energy due to friction, even tiny amounts from the very thin upper atmosphere, its orbit decays and it spirals inward. According to classical physics, the electron in its orbit is constantly radiating light, constantly losing energy. The calculations were brutal. That electron should spiral down into the nucleus in a tiny, tiny fraction of a second, something like 100 millionth of a second. All atoms should collapse almost instantly. Matter as we know it, solid tables, flowing water, living beings, should simply not exist. The universe should be a featureless soup of collapsed atoms. But your table is solid. You are reading this. Atoms are stable. Hydrogen atoms have been happily humming along for billions of years, their electrons steadfastly not crashing into the proton. This wasn't just a disagreement between theory and a lab experiment. It was a screaming contradiction between classical physics and the very existence of the stable universe we inhabit. The grand clockwork, when applied to the atom, predicted its own instant annihilation. This was more than a squeak. It was the sound of a critical mainspring snapping. The classical model of the atom was fundamentally, fatally broken. It couldn't explain the basic stability of the building blocks of everything. These three problems, the ultraviolet catastrophe, the photoelectric effect, and atomic stability, weren't isolated quirks. They were gaping cracks in the foundation of classical physics. They weren't failures at the edges. They struck right at the core principles governing energy, light, and the structure of matter. The universe, under this intense new scrutiny, was refusing to follow the old, comfortable deterministic rules when things got very small or energies got very high. The equations that perfectly described planets and steam engines produced nonsense when applied to atoms and light emission. It was a crisis. Physics was like a ship that had confidently navigated oceans, suddenly finding its charts useless in a strange new sea. The beautiful, predictable clockwork universe was grinding to a halt. The physicists of the time knew it. There was a palpable sense of unease, of excitement, of frustration. The old rules weren't enough. Something radical, something utterly new, was needed. The stage was set not for a minor adjustment, but for a full-blown revolution in our understanding of reality. The quantum era was dawning, born from the profound failure of the classical world to explain its own innermost workings. The comfortable predictability was about to give way to a world of probability, fuzziness, and unimaginable strangeness, all to make sense of why your toaster doesn't vaporize you, why blue light unlocks electrons but red light doesn't, and why the very atoms holding you together don't just instantly implode. The cracks in the clockwork were the birth cries of a whole new physics. Imagine the scene, the dawn of the 20th century. Physics, that grand old clockwork universe, is shuddering. The ultraviolet catastrophe screams that hot objects shouldn't just glow warmly. They should incinerate us with invisible rays. The photoelectric effect mocks the wave theory of light, acting like a lock that only accepts blue keys, no matter how hard you shake a red keychain. And worst of all, atoms themselves, the very building blocks of everything, should collapse in a cosmic blink, according to the cherished laws of electromagnetism. Yet here we are, solid and stable. The physicists aren't just puzzled, they're deeply unsettled. The foundations are cracking. Something radical is needed. Something that throws out centuries of ingrained intuition about how energy and matter behave. This isn't the time for a gentle tweak. It's time for revolution. And revolutions rarely start with a single shout. They begin with desperate whispers, bold leaps into the unknown, and models built on shaky scaffolding that somehow hold long enough for the next builder to arrive. Enter Max Planck. Picture him, a meticulous conservative German physicist in 1900, deeply steeped in the classical tradition. He wasn't out to overthrow physics. He was just trying to fix a specific embarrassing problem, the ultraviolet catastrophe. The equations describing how a hot object radiates energy, based purely on classical thermodynamics and wave theory, were giving that nonsensical infinity result. It was like a beautiful recipe for cake that, when followed exactly, produced a toxic sludge instead. Planck wrestled with it. He knew the experimental data was right. The infinity prediction had to be wrong. So, in a move that must have felt almost sacrilegious, he made a desperate, purely mathematical gamble. He proposed that the atoms in the hot object couldn't radiate energy in just any amount, like water flowing smoothly from a tap. Instead, he suggested, they could only emit energy in tiny, specific, indivisible packets. He called these packets quanta, from the Latin for how much. Think of it like this. Instead of being able to pour any amount of water, you could only hand out energy in pre-filled tiny bottles. Each bottle, or quantum of energy, had a size directly linked to the frequency of the light being emitted. HF, E is equal to H multiplied by H. Here, E is the energy of the packet, F is the frequency of the light, how fast it wiggles. Blue light wiggles faster than red. And H is a new, incredibly tiny constant of nature we now call Planck's constant. This wasn't some grand philosophical statement about the nature of reality. Planck didn't wake up believing the universe was granular. It was a last-ditch mathematical trick, a way to force the equations to stop predicting infinity and instead match the actual experimental curves of blackbody radiation. And astonishingly, it worked perfectly. The infinity vanished. The equations now beautifully described how a hot object glows red, then white, then blue as it heats, with the energy dropping off sharply at high frequencies, ultraviolet and beyond, just as experiments showed. But Planck himself was deeply uncomfortable. He saw his constant as a necessary mathematical fudge factor, not a revelation about the universe. He spent years trying to reconcile his quantum idea back into classical physics, believing the continuous wave view must be correct underneath. He'd sown the seed of quantum theory almost by accident, watering it with reluctance. He'd shown energy came in lumps for emission and absorption by matter, but he still clung to the idea that light itself, traveling through space, was a continuous wave. The seed was planted, but it was buried deep, and its revolutionary nature wasn't yet fully grasped, even by the gardener. 5 years later, across Europe, a young patent clerk in Switzerland, Albert Einstein, looked at Planck's curious idea and the baffling photoelectric effect, and saw something Planck hadn't dared to. Einstein, even then, had a fearless intellect, unafraid to challenge established dogma. Where Planck saw a mathematical fix for matter, Einstein saw a fundamental truth about light itself. The photoelectric effect was the key. Classical wave theory insisted that brighter light, more intense waves, should deliver more energy to the electrons in the metal, so brighter light should kick out electrons with more energy. But experiment said no. Brighter light only kicked out more electrons. Their individual energy depended only on the color frequency of the light. Dim blue light gave electrons the same energy as bright blue light. Intense red light gave nothing. Einstein made a breathtaking leap. He took Planck's quantum of energy, HF, and declared it wasn't just about how atoms absorbed or emitted energy, but about the very nature of light. He proposed that light itself isn't just a wave. Sometimes it behaves as if it's made of discrete particles, little bullets of energy. He called these particles light quanta. We now call them photons. Each photon, Einstein said, carries one quantum of energy, E to F. So, a blue photon, high frequency F, packs a bigger energy punch than a red photon, lower frequency F. Suddenly the photoelectric effect made perfect, elegant sense. It wasn't about waves washing over the metal. It was like shooting tiny energy bullets at it. To knock an electron loose, you need a single bullet, photon, with enough energy to overcome the electron's bind to the metal, a threshold energy later called the work function. A red photon, HF red, even if there are millions of them, bright red light, doesn't have enough individual energy to knock out an electron. It's like trying to break down a door by throwing millions of fluffy pillows at it. No single pillow has the required oomph. But a single blue photon, HF blue, even if it's the only one hitting the metal, dim blue light, does have enough energy. Wham! Electron ejected. Brighter blue light just means more blue photons, so more. Electrons get knocked out, but each one gets hit by a single photon carrying energy, HF blue, so they all fly off with roughly the same maximum energy. The energy of the ejected electrons depends only on the frequency, which sets the photon energy, HF, and the work function of the metal, not the intensity. Einstein had solved the puzzle by giving light a split personality, wave-particle duality. It could act like a spread-out wave, explaining interference, diffraction, or like a localized particle, explaining the photoelectric effect, depending on the experiment. This was revolutionary and deeply unsettling. It was like saying a ball could sometimes be a hard sphere and sometimes a spread-out wave on a pond. Planck's mathematical trick was now a proposed physical reality, and Einstein was boldly applying it to light itself, challenging the wave theory that had reigned supreme since Huygens and Young. This wasn't a reluctant gambit, it was a visionary charge. Einstein received the Nobel Prize for this work, not for his more famous relativity theories. It was that important. Now, fast forward to 1913. The atom is still a cosmic scandal. Rutherford has shown it has a tiny, dense nucleus with electrons whizzing around it. But classical physics insists those electrons should be radiating away their energy as light and spiraling into the nucleus in an instant. Enter Niels Bohr, a young Danish physicist working in Rutherford's lab. Bohr was fascinated by the structure of the atom and also by the strange, precise patterns seen in atomic spectra. When you heat a gas like hydrogen, it doesn't glow with a continuous rainbow. Instead, it emits light only at very specific, sharp frequencies, distinct lines of color, like a cosmic barcode. Each element has its own unique set of lines. Classical physics couldn't explain this either. Accelerating electrons should emit a continuous smear of all frequencies, not distinct lines. Bohr looked at Rutherford's nuclear atom, Einstein's photons, and Planck's quanta, and took another audacious step. He proposed a semi-classical model, specifically for the simplest atom, hydrogen. He kept the planetary picture, electrons orbiting the nucleus, but imposed radical new quantum rules, quantized orbits. Bohr declared that electrons cannot orbit at just any distance from the nucleus. They can only exist in specific, allowed circular orbits. Think of it like a ladder. The electron can stand on rung 1, rung 2, rung 3, etc., but it cannot stand between the rungs. Each orbit has a specific fixed energy. The lowest orbit, closest to the nucleus, has the lowest energy. Orbits farther out have higher energy. Stationary states. Here's the truly bizarre part that defied Maxwell. Bohr stated that while an electron is in one of these allowed orbits, it does not radiate any energy at all. It's stable. This was a direct violation of classical electromagnetism, but it was the only way to explain why atoms didn't collapse. The orbits themselves were magically stable. He called these stable configurations stationary states. Quantum jumps photons. How does an atom absorb or emit light? Bohr said the electron can instantly jump from one allowed orbit to another. It doesn't glide smoothly. It vanishes from one orbit and reappears in another in a quantum leap. If it jumps down from a higher energy orbit to a lower energy orbit, the atom must get rid of the excess energy. It does this by emitting a single photon. Crucially, the energy of that photon is exactly equal to the energy difference between the two orbits. Conversely, to absorb light and jump up to a higher orbit, The atom must absorb a photon whose energy exactly matches the difference between the orbits. This model was a hybrid, a Frankenstein monster of classical orbits grafted onto quantum rules. But it worked spectacularly well for hydrogen. It explained the stability of the atom. Electrons lived happily in their lowest orbit, the ground state, or higher orbits without radiating away energy and collapsing, only interacting when jumping between states. Most brilliantly, it explained the mysterious spectral lines. Each line in hydrogen's spectrum corresponded exactly to the energy difference, HF, between two specific orbits in Bohr's model. The electron jumping from orbit 3 to orbit 2 emitted one specific photon, one specific color. Jumping from 4 to 2 emitted another photon of a different energy, a different color, and so on. The discrete lines were direct evidence of the discrete energy levels. Bohr had introduced the concept of quantized energy levels. For bound systems like atoms, energy wasn't just emitted in packets, it was stored in the atom in specific quantized amounts, depending on which orbit the electron occupied. The jump between levels absorbed or emitted a photon carrying precisely that quantized energy difference. He also showed that the angular momentum of the electron in these orbits was quantized in units of Haar, h-bar, Planck's constant divided by 2p, adding another layer of quantum granularity. The foundations weren't just shaking now. They were crumbling and being rebuilt with strange new bricks. Planck had shown energy exchange was granular EDHF. Einstein showed light itself could be particle-like, photons carrying EEDF. Bohr showed that within the atom, energy states themselves were granular, quantized levels, and changes happened in instantaneous jumps emitting, absorbing photons. The universe, at its core, was revealing itself to be chunky, discontinuous, digital in its fundamental transactions, not the smooth, continuous analog picture classical physics had painted. It was granular, not continuous. This was the dawn. Planck, Einstein, and Bohr, each driven by confronting a specific failure of the old physics, had laid the groundwork. Planck's reluctant quanta, Einstein's bold photons, and Bohr's stabilizing quantum leaps and levels created a patchwork solution that worked for specific, critical problems. But it was still incomplete, slightly inconsistent, and deeply weird. Why were orbits stable? What was an electron really doing? How did it jump? The wave-particle duality was still a confusing paradox. The full, bizarre, probabilistic machinery of quantum mechanics, the wave functions, the uncertainty principle, the profound role of probability, was still hidden in the wings, waiting for the next generation, Heisenberg, Schrödinger, Born, Dirac, to step onto the stage and reveal the truly mind-bending nature of the quantum world. But the revolution had begun. The cracks in the clockwork couldn't be plastered over. They demanded a whole new kind of timepiece, one that ticked to the rhythm of quanta, photons, and quantum leaps. The comfortable certainty was gone, replaced by a strange, granular, and exhilarating new frontier. The Bohr model was just the beginning, a stepping stone. The full quantum mechanics developed in the 1920s, Heisenberg's matrix mechanics, Schrödinger's wave mechanics, later shown to be equivalent, was far stranger and more powerful. Imagine stepping through a looking glass, not into a world of talking rabbits, but into a realm where the very rules of reality seem rewritten by a whimsical, slightly mischievous genius. That's the full quantum world, far beyond Bohr's tentative steps. The 1920s weren't just about flapper dresses and jazz. They witnessed an intellectual explosion that reshaped our understanding of existence. Think of Bohr's model as a rough sketch. What came next? Heisenberg's matrix mechanics and Schrödinger's wave mechanics. Mathematically equivalent, just different perspectives, was the full, mind-bending Technicolor painting. And its core principles? They're less like sturdy pillars and more like shimmering, paradoxical mirages that somehow form the bedrock of everything. Let's dive into this beautiful, baffling weirdness. Wave-particle duality, the ultimate identity crisis, but for everything. Remember Einstein's photon, light acting like a particle, and how light also clearly acts like a wave, creating interference patterns, like overlapping ripples creating dark and bright bands. That was confusing enough. But hold on to your hat. This split personality isn't just for light. Everything has it. Electrons, protons, atoms, even whole molecules made of 60 carbon atoms, buckyballs, named after Buckminster Fuller's geodesic domes, have been shown to exhibit wave-like behavior under the right conditions. Forget the tiny, hard billiard ball electron orbiting the nucleus like a planet. In the full quantum picture, an electron is more like a fuzzy cloud of possibilities, a ghostly smear of could-be-here-ness. This is described mathematically by Erwin Schrödinger's wave function, often denoted by the Greek letter psi-6. Think of the wave function as a complex, wavy pattern spread out through space. But here's the kicker. This wave function doesn't tell you where the electron is. Instead, the square of its magnitude, bars 2, at any point gives you the probability of finding the electron there if you look for it. So before you look, the electron isn't somewhere specific. It's spread out, like a wave, existing in a haze of potential locations. It's a probability wave. It could be here or there or over there with varying likelihoods. But the moment you poke it, the moment you make a measurement, say by hitting it with a photon to see where it is, something dramatic happens. That spread out wave function instantly collapses. It shrinks down, vanishing from all those other possible locations, and you find the electron right here, a definite whole particle sitting at one specific point. Poof. The wave becomes a particle upon observation. This is profoundly counterintuitive. It means the electron, or any quantum object, isn't fundamentally a particle or a wave. It's something more elusive, a quantum entity that manifests as one or the other, depending entirely on how you choose to interact with it. Ask it a "where are you?" question, a position measurement, and it snaps into a particle-like state at a specific spot. Ask it a "how are you moving?" question. Observe its momentum or wavelength via interference, and it shows its wave-like nature, spreading out and interfering with itself. The act of observation isn't just seeing, it's forcing the system to pick a role. It's like a chameleon that becomes rock solid when you try to grab it, or liquid when you try to pour it, depending on what you do. The universe, at its core, is context-dependent. This duality is the first, deep strangeness you have to embrace. Quantization, the universe's staircase, no ramps allowed. Planck stumbled upon it with energy packets. Bohr built it into his atom with fixed orbits. The full quantum theory makes it universal. Quantization. Forget smooth, continuous changes for many fundamental properties. In the quantum realm, things come in distinct, separate chunks, like climbing a staircase. You can stand on step 1, step 2, or step 3, but you can't hover magically between steps. There are no ramps for these properties. Energy. This is the classic. Electrons in an atom don't have any energy they please. They occupy specific energy levels, like rungs on a ladder. Jumping between these levels absorbs or emits a photon with energy exactly equal to the difference. This is why atomic spectra aren't smeared rainbows, but sharp, distinct lines. Each line corresponds to a specific jump between specific energy rungs. A photon isn't just a packet. Its energy itself is quantized based on its frequency. EHF. Angular momentum. Think of how fast something is spinning and how spread out its mass is, like an ice skater pulling arms in to spin faster. For electrons in atoms and other quantum particles, their orbital angular momentum, related to which Bohr orbit they'd be in, can only take on values that are whole number multiples of h bar, Planck's constant h, divided by 2p. No fractions allowed. 0, h, 2 hairs, 3h. That's it. Spin. This is perhaps the weirdest quantized property. It's often described as a particle's intrinsic angular momentum, as if it were spinning, but crucially, it's not actually spinning. Like a tiny ball, it's a purely quantum property with no direct classical analogy, and it's quantized in the simplest way possible. For electrons, protons, and neutrons, spin can only be plus 1 more 2h or being 1 more 2h, and often called spin up or spin down. It's a fundamental binary property baked into each particle. Imagine a coin that can only be found heads up or tails up when you look. But before you look, it might be in a weird mix of both, thanks to superposition. This inherent chunkiness is fundamental. Energy, momentum, angular momentum, spin. They don't flow like water. They click like gears shifting between specific discrete settings. The universe is digital at its most fundamental level. The uncertainty principle. Werner Heisenberg gave us perhaps the most famous and philosophically unsettling principle in physics. The uncertainty principle isn't about clumsy scientists or bad equipment. It's a fundamental limit on what we can know about the universe itself. It states, simply yet profoundly, you cannot simultaneously know both the exact position, x, and the exact momentum, p, of a particle. The more precisely you pin down where it is, the less you can possibly know about how fast it's going and in what direction, its momentum. Conversely, the more precisely you know its momentum, the fuzzier its position becomes. It's not a measurement error. It's baked into reality. This equation for the uncertainty principle says the product of the uncertainties in position and momentum must always be greater than or equal to h bar over 2. If you know position very precisely, momentum must get larger. It means momentum becomes very uncertain, and vice versa. Why? Think of 2 ways. The photon kick. To see where an electron is, you have to bounce something off it, like a photon. But that photon carries momentum. When it hits the electron, it gives it a random kick, changing its momentum in an unpredictable way. The more precisely you want to know the position, using a higher energy, shorter wavelength photon for better focus, the bigger the kick, and the more you mess up the momentum. The wave function nature. This is the deeper reason. Remember the wave function? A particle with a very well-defined position has a wave function that's a sharp, narrow spike. But mathematically, such a sharp spike is actually made by adding together a wide range of different waves, each with a slightly different wavelength and momentum. So, a precise position means a broad spread of possible momenta, high uncertainty in momentum. Conversely, a particle with a very well-defined momentum has a wave function that's a long, smooth wave with a single, precise wavelength. But such a wave is spread out over a large region of space. So, precise momentum means a broad spread of possible positions, high uncertainty in position. The wave function, physically, cannot be both sharply peaked in position and have a single, precise wavelength. The uncertainty principle is a direct consequence of the wave nature of matter. The universe has a fundamental fuzziness. It's not that things are precise and we just can't measure them. At the quantum level, precision in one property requires fuzziness in another. It's a feature, not a bug. Quantum superposition, Schrödinger's cat and the art of being. Two things at once until you look. This is where things get truly bizarre. The heart of quantum weirdness. Superposition means that before you measure it, a quantum system doesn't have to be in just one definite state. It can exist in a combination of multiple possible states simultaneously. It's not maybe here, maybe there. It's both here and there, or both, spinning up and spinning down at the same time. Erwin Schrödinger, disturbed by the implications of the emerging quantum theory, devised a famous and infamous thought experiment to highlight the absurdity he saw if you applied quantum rules to large objects. Schrödinger's cat. Imagine placing a cat inside a sealed steel box. Also, inside is a tiny bit of radioactive material, say a single atom of uranium-235. Uranium atoms decay randomly via quantum processes. There's a 50-50 chance this atom will decay within, say, 1 hour. There's a Geiger counter aimed at it. If the Geiger counter detects a decay, a single particle emitted, it triggers a mechanism. A hammer falls, smashing a vial of deadly poison gas. If the atom decays, the cat dies. If it doesn't decay, the cat lives. Now close the box. Wait 1 hour. What's the state of the cat? According to the strict rules of quantum mechanics as applied to the radioactive atom. The uranium atom is governed by quantum probability. After 1 hour, it is not definitely decayed or not decayed. It exists in a superposition nuance of states, decayed and yet not decayed. The Geiger counter is set to trigger if decay happens. But since the atom is in both states, the Geiger counter must also be in a superposition, triggered and not triggered. The hammer must be fallen and not fallen. The poison vial smashed and intact. Therefore, the poor cat must be in a superposition of alive and dead. Only when you open the box and look, when you make a measurement, does this superposition instantly collapse. You see the cat definitively alive or definitively dead. The act of observation forces the entire system into one classical reality. Schrödinger meant this as a reductio ad absurdum, arguing that the idea of superpositions applying to cats was ridiculous, so the quantum theory must be flawed or incomplete. But here's the twist. While we don't put cats in such boxes, thankfully, superposition is undeniably real for quantum systems. An electron shot through a barrier with 2 slits doesn't go through one slit or the other. Its wave function goes through both slits simultaneously, interferes with itself on the other side, creating a wave-like interference pattern on a detector screen. Only when it hits the screen measurement does it appear as a single particle at one point. An electron's spin isn't definitely up or down until you measure it. Before measurement, it can be in a superposition of both spin states. You can even set up experiments where it's spinning both clockwise and counterclockwise, relative to different axes at the same time. Photons can be polarized both horizontally and vertically simultaneously until measured. Superposition is the rule, not the exception, for unobserved quantum systems. Reality at the quantum level is a shimmering haze of possibilities, a blend of could-bes, only snapping into a definite is when we interact with it. It's like a dice tumbling through the air. It's not secretly a 3 or a 5. It's genuinely in a state representing all possibilities at once, only becoming a single number when it lands and stops moving. The measurement. The quantum dice is always tumbling until you look. Quantum entanglement. Spooky twins across the universe. If superposition is weird, entanglement is downright spooky. Albert Einstein, deeply troubled by the implications of the new quantum mechanics, derisively called it spooky action at a distance. He hoped it was proof the theory was incomplete. But decades of meticulous experiments have proven Einstein wrong on this one. Entanglement is real, and it's one of the strangest phenomena in nature. Here's how it works. Imagine a process that creates two particles, like two electrons or two photons, together in a single unified quantum state. For example, a particle decaying into two photons flying off in opposite directions. Because they were created together, their quantum properties become intrinsically linked, or entangled. They are no longer separate, independent entities. They form a single, inseparable quantum system, even if they drift apart. The entanglement often links specific complementary properties. For instance, the spins of two electrons might be entangled such that if one is measured to be up, the other must be down, and vice versa. Or the polarizations of two photons might be linked. If one is horizontal, the other is vertical. The key point is that the state of each particle is undefined until measured, but they are perfectly correlated. Now, let these two entangled particles fly apart. Take one to your lab in New York. Send the other to a lab on Mars. Keep them completely isolated from any outside influence that could talk to them. Now the scientist in New York measures the spin of their electron. Instantly, randomly, they get up or down, say up. At that exact instant, the spin of the electron on Mars becomes definitively down. Not later, not after a signal travels. Instantly, the measurement on one particle, forced. The other particle, light years away, into the opposite state. It's as if the particles share a single existence, no matter the distance. Measuring one tells you the state of the other, and, according to the theory, determines it at that moment. This seems to violate Einstein's own theory of relativity, which sets the speed of light as the universe's ultimate speed limit. How can information about the measurement, which spin was found, seemingly travel faster than light to affect the distant particle? Here's the crucial caveat, the saving grace that prevents paradoxes and faster-than-light communication. You cannot use entanglement to send a message faster than light. Why not? Think about the scientist on Mars before the New York measurement. They look at their entangled electron. What do they see? They see a completely random result. They have a 50-50 chance of measuring spin up or spin down. They see no change in their particle when the measurement happens in New York. They don't know what state their particle is in until they measure it, and when they do, it's random. Only after both scientists measure their particles and then get on the phone, or radio slower than light, to compare notes do they discover the perfect correlation. I got up. Oh, I got down. Or I got down. I got up. Every time. The spooky action instantly sets the correlation between the particles, but it doesn't transmit any usable information or control from one place to the other. The outcome for each measurement is still random and unpredictable locally. It's like having two sealed envelopes. You know one contains A and the other B, but you don't know which is which. You take one envelope to New York, the other to Mars. You open yours in New York and find A. You instantly know the envelope on Mars contains B. But the person on Mars, looking at their still sealed envelope, has no idea what's inside or that you've opened yours. Only when you call and tell them you found A do they know theirs is B. The knowledge that the envelopes are correlated existed when they were prepared and sealed together. The act of opening one doesn't physically change the other envelope. It just reveals the pre-existing correlation. Quantum entanglement is like that, but the correlation isn't set until the first measurement happens, and it happens instantaneously across any distance. The envelopes are in a superposition of New York, a Mars, B, and New York, B Mars A, until one is opened. Experiments have confirmed entanglement over distances exceeding 1,000 kilometers, even using satellites, closing loopholes that Einstein and others proposed. This spooky connection is a fundamental feature of quantum mechanics. It hints that the universe might be far more deeply interconnected than our classical, local reality suggests. Entangled particles, once linked, remain parts of a single, non-local quantum entity, defying our everyday notions of separate objects in distinct locations. It's a profound mystery and the cornerstone of emerging technologies like quantum computing and quantum cryptography. This is the full quantum strangeness, particles that are also waves, existing in multiple places or states at once until observed, with properties that are fundamentally fuzzy and linked instantaneously across vast distances. It's a world governed by probability waves, not certainties. It rejects the classical clockwork for a dynamic, probabilistic dance. The wave function Weimses is the star, evolving smoothly according to Schrödinger's equation, a deterministic wave of possibilities, until the jarring moment of measurement, the collapse, where probabilities crystallize into a single, definite outcome. Why and how this collapse happens, the measurement problem, remains one of the deepest unsolved puzzles. Yet this bizarre, counterintuitive framework isn't just abstract philosophy. It works spectacularly well. It predicts atomic behavior with incredible precision, explains chemical bonds, powers lasers and semiconductors, and underpins our modern technological world. The quantum world is undeniably strange, a constant challenge to our intuition forged in the macroscopic realm of balls and planets. But by embracing this weirdness, the duality, the quantization, the uncertainty, the superposition, and the spooky entanglement, we unlock the deepest secrets of how the universe truly operates at its most fundamental level. It's a world where cats can be both alive and dead, dice are always tumbling, and particles whisper to each other across the void. A world far stranger and more wonderful than we could have ever imagined from the comfortable predictability of the classical stage. The quantum revolution didn't just change physics, it changed our understanding of reality itself. And the dance continues. The sheer, comfortable predictability of our everyday world, the arc of a thrown baseball, the steady tick of a pendulum clock, the warmth of sunlight on your skin, feels utterly divorced from the quantum craziness we just explored. Why don't baseballs spontaneously tunnel through brick walls? Why isn't your coffee cup simultaneously here and slightly over there? Why does cause and effect feel so absolute, not probabilistic? This seamless transition from the bizarre quantum underworld to our familiar classical reality is one of physics' most profound and elegant insights, captured by Niels Bohr's correspondence principle. It tells us that quantum mechanics doesn't contradict classical physics. It contains it. Classical physics isn't wrong. It's an incredibly precise approximation that emerges naturally when things get big, heavy, and messy. Let's unpack why. Imagine a single electron. Its wave function might be spread out over a region the size of an atom, a significant fuzziness. The uncertainty principle tells us we can't precisely know both its position and momentum. It could easily be in a superposition of states, or even quantum tunnel through a thin barrier. Its behavior is inherently probabilistic and spread out. Now consider a baseball. It contains roughly 10 to power 25 atoms. That's a 1 followed by 25 zeros. Each atom contains electrons and a nucleus, all governed by quantum rules. So, isn't the baseball just a gigantic quantum object? Shouldn't it exhibit massive superposition and uncertainty? The answer lies in scale, mass, and interaction. The three keys to the correspondence principle. Scale numbers, the law of large numbers. Think of the baseball's overall position. Each individual atom has its own wave function, with its own uncertainty about where it is. But these uncertainties are random. Some atoms might be slightly here, others slightly there, relative to the baseball's center of mass. Averaging over 10 to power 25 randomly fluctuating positions is like flipping a coin, 10 to power 25 times. You know with near-perfect certainty you'll get almost exactly 50% heads and 50% tails. The random fluctuations cancel each other out almost perfectly. The average position of all those atoms, the center of mass of the baseball, becomes incredibly sharp and well-defined. The wave function describing the baseball's overall position is not spread out like an electron's. It's an incredibly narrow, sharply peaked spike, centered exactly where your eyes see it. The uncertainty in its position, delta x, is fantastically small, far smaller than the size of an atom, utterly negligible for any practical purpose. You know exactly where the ball is, classically speaking. Similarly, the random uncertainties in the momenta of all the individual particles average out to give the baseball's total momentum, p, mass times velocity, a very precise value. Delta p for the whole ball is minuscule. Mass, the heavy anchor. Planck's constant in the uncertainty principle is incredibly small, about 1.054718 multiplied by 10 to power minus 34 joule seconds. This means the inherent fuzziness is tiny on human scales. Momentum p is mass times velocity. For a light electron with mass 10 to power minus 30 kilogram, even a small uncertainty in velocity translates into a significant relative uncertainty. For a baseball with mass 0.15 kilogram, the same translates into an immeasurably small uncertainty in velocity. Because the mass m is so large, uncertainty is vanishingly small. The baseball's velocity is effectively certain. Quantum effects like tunneling depend exponentially on the mass. The probability for a single electron to tunnel through a barrier might be significant. The probability for all 1025 atoms in a baseball to tunnel coherently, in the same way at the same time, through a wall is so infinitesimally small that it would take many times the current age of the universe to observe it happening, even once. It's effectively zero. Interaction. Decoherence. This is perhaps the most crucial factor for killing quantum weirdness in big objects. The baseball isn't floating alone in a perfect vacuum. It's constantly bombarded by trillions of air molecules every second. Photons of light are bouncing off it. It's in contact with the air, maybe your hand, the ground. Every single collision with an air molecule, every photon bouncing off it, is effectively a tiny measurement. Remember what happens during measurement in quantum mechanics? Superpositions collapse. Wave functions get pinned down. For our hypothetical baseball in a superposition of here and slightly over there, the very first air molecule that bumps into it interacts differently depending on where the ball actually is in that superposition. This interaction entangles the baseball's position state with the state of the air molecule. Information about the baseball's position leaks out into the environment via that molecule. This process is called decoherence. It happens incredibly rapidly, unimaginably faster than a blink of an eye for any macroscopic object. The environment acts like a relentless observer, constantly measuring the object, continuously collapsing any budding superpositions before they have a chance to develop or be observed. The baseball simply doesn't have time to exist in a quantum superposition of locations. The environment forces it to pick a definite here almost instantly. Decoherence explains why Schrödinger's cat isn't in a superposition. The cat isn't isolated. It's breathing. Its heart is beating. Molecules are jiggling within it. Photons are bouncing off it. Even in the dark, there's thermal radiation. The cat's alive state and dead state interact dramatically differently with the environment. Decoherence destroys the delicate superposition almost instantaneously, long before the box is opened. The cat is either alive or dead well before you look. Quantum mechanics is fundamentally probabilistic. We calculate probabilities for outcomes. So how does the deterministic certainty of classical physics, throw the ball at 20 meters per second at 30 degrees and it will land exactly here, emerge? Averaging, again. The baseball's trajectory is the average path of its trillions of constituent particles. Each particle's quantum jitter is random. Averaging over so many random fluctuations produces an incredibly smooth, predictable average path. The probability distribution for the baseball's center of mass position is so sharply peaked that it's indistinguishable from a single, certain path. The inherent quantum probabilities for the whole object become so sharply focused that they look like certainty. Ehrenfest's theorem. This mathematical gem of quantum mechanics shows that, under many conditions, the average your expected position and the average you expected momentum of a quantum system obey equations that look exactly like Newton's classical laws of motion, F m d2 2x dt 2o, where x is the average position. For the sharply peaked wave function of a large object, the average is the only value you'll ever see, and it follows Newton perfectly. Classical physics, a phenomenally good approximation. So, classical physics isn't some separate, competing theory. It's the emergent behavior of vast ensembles of quantum particles when you zoom out. It's the predictable, deterministic, continuous world that arises from the average of countless tiny, random, discrete, fuzzy quantum events. The correspondence principle assures us: 1. Predictions. Match. For systems where quantum effects are negligible, large, heavy, interacting objects, the predictions of quantum mechanics precisely match. The predictions of classical mechanics, electromagnetism, and thermodynamics. Quantum mechanics reduces to classical physics in this limit. 2. Useful domain. Classical physics remains incredibly powerful and accurate for describing the vast majority of phenomena we encounter daily. Engineering, planetary motion, fluid dynamics, most of chemistry, except the very details of bonding, thermodynamics of engines, etc. You don't need Schrödinger's equation to build a bridge or predict an eclipse. Newton and Maxwell suffice with stunning accuracy. 3. Fundamental foundation. Crucially, quantum mechanics provides the underlying reason why classical physics works so well. It explains the origin of the classical laws. Newton's F(ma) isn't a fundamental truth. It's a consequence of the quantum behavior of trillions of particles averaged together. Why your world makes sense. You throw the baseball. Its immense mass and size mean its quantum wave function is a needle-sharp spike in position and momentum space. Trillions of collisions with air molecules every nanosecond constantly measure it, decohering any hint of superposition, pinning it firmly to a definite location and velocity. The random quantum jitters of its atoms average out perfectly, making its path follow Newton's elegant parabola with near-perfect certainty. Quantum tunneling? Statistically impossible for something so massive and complex. Superposition? Destroyed by the environment faster than thought. The uncertainty principle? Still there, but so minuscule it couldn't budge the ball a fraction of an atom's width. The quantum weirdness hasn't vanished. It's still there, humming away inside every atom of the ball, and the air, and your hand. But its effects are drowned out by the sheer scale, mass, and noisy environment of the macroscopic world. The bizarre quantum tango continues unabated in the subatomic realm. But when you step back and look at the whole dance floor, at the baseball, the bridge, the planet, the motion resolves into the smooth, predictable waltz described by classical physics. Bohr's correspondence principle is the beautiful revelation that these two seemingly contradictory worlds are intimately connected, one emerging seamlessly and logically from the other, allowing us to navigate our human-scale reality with confidence while understanding the deeper, stranger symphony playing beneath the surface. The classical world works because of quantum mechanics, not despite it. Imagine stepping back from the dizzying dance of quantum particles and looking around. That phone in your pocket, the GPS guiding your drive, the laser reading your groceries, the MRI scan that saved a life, none of this is magic. It's quantum mechanics in action. This isn't some abstract puzzle confined to chalkboards and particle colliders. It's the invisible engine humming inside nearly every piece of modern technology, shaping our world in profound ways. Let's connect the dots between the bizarre quantum rules and the tangible reality we live in. 1. The Silicon Revolution, transistors, semiconductors. Forget vacuum tubes and clunky relays. The heart of your computer, phone, TV, car, microwave, virtually anything with smart in its name, is the transistor. And transistors work because of quantum mechanics. Silicon, the workhorse material, is a semiconductor. Its magic lies in the quantum energy bands. Think of electrons in a solid not as tiny planets, but as waves occupying specific energy bands, like floors in an apartment building. In silicon, there's a crucial gap, the band gap, between the almost full lower band, valence band, and the mostly empty upper band, conduction band. At absolute zero, electrons are stuck downstairs, but add a little energy, like heat or an electric field, and thanks to quantum mechanics, electrons can jump the gap. It's quantized, remember. They don't slowly climb, they quantum leap. By carefully adding tiny amounts of other atoms, doping, we create regions where electrons are plentiful, n-type, or scarce, leaving holes that act like positive charges, p-type. Sandwiching these regions creates a transistor. Applying a tiny voltage to one part, the gate, controls the quantum flow of electrons or holes between other parts, source and drain, acting as an incredibly fast, efficient switch or amplifier. Billions of these quantum switches etched onto tiny chips are your computer's brain. Without understanding the quantum behavior of electrons in these crystal lattices, the band structure, the tunneling, the doping effects, none of this miniaturization or power would be possible. The digital age is fundamentally the quantum age. 2. Coherent light, lasers. Ordinary light is a chaotic mess, photons flying out randomly in all directions out of phase, like a crowd shouting incoherently. A laser. Light amplification by stimulated emission of radiation is light disciplined by quantum rules. It relies on stimulated emission, a purely quantum phenomenon predicted by Einstein. Imagine an atom in an excited state, electron in a higher energy orbit. Normally, it decays spontaneously, emitting a random photon. But if a photon of exactly the right energy, E, HF, matching the atom's energy gap, passes by, it can stimulate the atom to emit another photon. Crucially, this new photon is identical to the first one. Same energy, same direction, same phase. It's like the first photon says, "Copy me." Inside a laser cavity, mirrors at each end, this creates a chain reaction. One stimulated emission triggers another and another. Photons bounce back and forth, stimulating more and more perfectly synchronized copies. One mirror is partially transparent, letting a powerful, coherent beam escape. All the photons marching in lockstep, like a perfectly synchronized light army. This coherence, all waves perfectly aligned, enables everything from delicate eye surgery and DVD players to high-speed internet fiber optics and laser pointers. It's quantum precision harnessed for light. 3. Seeing inside. MRI scanners. Magnetic resonance. Imaging is a medical marvel that lets doctors see soft tissues in incredible detail without harmful X-rays. Its heart is the quantum property of SOD nuclear spin. Protons in the nuclei of hydrogen atoms, abundant in water and fat in your body, act like tiny magnets with spin. Remember, +1,2H or 1,2HA. Normally their spins are random, but inside the powerful magnetic field of an MRI machine, quantum rules dictate they can only align with and or against the field, two discrete energy states. A pulse of radio waves, with energy HF precisely matching the energy gap between these spin states, flips some spins. When these spins flip back, they emit faint radio signals. Crucially, the frequency of this signal is exquisitely sensitive to the proton's local chemical environment. By detecting these quantum spin flip signals from millions of hydrogen atoms and using powerful computers to map their locations and environments, the MRI builds a detailed picture of your insides. It's literally listening to the quantum whispers of your body's atoms. 4. Ultimate timekeepers, atomic clocks. Ever wondered how GPS pinpoints your location so precisely? It relies on incredibly accurate timing, down to nanoseconds. That timing comes from real atomic clocks. They exploit the ultimate quantum metronome, the energy difference between two specific, hyperfine quantized energy levels in an atom, like cesium or rubidium. Microwave radiation is tuned exactly to the frequency F, corresponding to that energy gap, E, HF. When the frequency is perfect, atoms readily absorb the radiation and jump between the levels. This resonance is detected. The clock locks onto this frequency. Since the energy gap is a fundamental, unchanging quantum property of the atom, This frequency is incredibly stable. The best atomic clocks, often using laser-cooled atoms in near-perfect isolation to minimize environmental jitter, are so precise they would lose less than a second over the entire age of the universe. This quantum precision underpins global navigation, GPS, Galileo, synchronizes the internet, and tests fundamental physics theories. 5. Frictionless flow, superconductors. Imagine electricity flowing through a wire with zero resistance, no heat loss, no energy waste. That's superconductivity. A dramatic quantum effect occurring in certain materials at very low temperatures. The classical picture of electrons bumping into atoms, causing resistance, breaks down. Instead, electrons pair up into Cooper pairs, thanks to an interaction with vibrations in the crystal lattice, phonons. These pairs aren't like two billiard balls stuck together. They act as a single quantum entity with integer spin, a boson. Crucially, all Cooper pairs can condense into the same quantum ground state, a macroscopic quantum wave function. This allows them to flow coherently, without scattering, through the lattice. They essentially quantum tunnel en masse through the material unimpeded. Beyond lossless power grids, a future dream, superconductors enable incredibly powerful electromagnets for MRI machines, particle accelerators like the LHC, and super-sensitive quantum sensors, SQUIDs. 6. Light from electrons, LEDs, solar cells. Light-emitting diodes, LEDs, and solar cells are two sides of the same quantum coin, harnessing interactions between light and semiconductors. In an LED, you push electrons and holes together across a p-n junction. When an electron quantum leaps down from the conduction band to fill a hole in the valence band, the energy difference is released as, you guessed it, a photon. The color, frequency of the light is precisely determined by the size of the band gap. E photon cheers E gap. Quantum mechanics dictates the emission. Solar cells work in reverse. A photon from sunlight with energy greater than the band gap, E photon E gap, strikes the semiconductor. It can be absorbed, giving its energy to an electron, kicking it up from the valence band to the conduction band, creating an electron-hole pair. The built-in electric field of the p-n junction then sweeps these charges apart, generating an electric current. Quantum mechanics governs the absorption process and the energy conversion efficiency. Both technologies rely on the quantum nature of light and the quantized energy levels in solids, the quantum foundation of everything else. Chemistry is applied quantum mechanics. Why does carbon form 4 bonds? Why is gold shiny and inert? Why does the periodic table have its structure? The answers lie entirely in the quantum behavior of electrons. Electrons occupy quantized orbitals around nuclei, following the Pauli exclusion principle. No two electrons in the same atom can have identical quantum numbers. The shapes and energies of these orbitals, S, P, D, F, determined by solving Schrödinger's equation for atoms, dictate how atoms bond, how molecules form, and how they react. Chemical bonds themselves are quantum phenomena, sharing electrons, covalent, or transferring them, ionic, based on orbital overlaps and energy minimization. Understanding chemistry without quantum mechanics is like trying to build a house without knowing about atoms. Nuclear power particles. What holds the nucleus together against the fierce repulsion of protons? The strong nuclear force, described by quantum chromodynamics, QCD, a quantum field theory where quarks exchange gluons. Radioactive decay, alpha, beta, gamma. is fundamentally quantum tunneling and transitions governed by quantum probabilities. Nuclear reactors and bombs harness the energy released from quantum rearrangements within nuclei, fission or fusion. Particle physics, exploring the fundamental constituents of matter, quarks, leptons, and forces, mediated by gauge bosons like photons, gluons, WZ bosons, is built entirely on the framework of quantum field theory, QFT, the marriage of quantum mechanics, special relativity, and field concepts. It's quantum mechanics all the way down. The quantum horizon, beyond theory, into technology. The quantum revolution isn't over. It's accelerating into new frontiers. 1. Quantum computing. Harnessing the weirdness directly. Classical computers use bits, 0 or 1. Quantum computers use qubits. A qubit exploits superposition. It can be 0, 1, or both, 0 and 1 simultaneously. Entangle multiple qubits, and they represent a vast number of possibilities, all at once. Performing calculations on this quantum parallelism could solve problems intractable for classical supercomputers, simulating complex molecules for drug discovery, optimizing logistics nightmares, cracking certain encryption codes, Shor's algorithm. It's incredibly challenging. Decoherence is the enemy, but progress is rapid. 2. Quantum cryptography. Using quantum rules for ultimate security. Quantum key distribution, QKD, like the BB84 protocol, exploits the no-cloning theorem. You can't perfectly copy an unknown quantum state and the disturbance caused by measurement. If an eavesdropper tries to intercept the quantum key, e.g., photons encoded in different polarization bases, their measurement unavoidably disturbs the states, alerting the legitimate users. It offers theoretically unbreakable security based on the laws of physics, not computational difficulty. 3. Quantum sensors. Exploiting quantum superposition and entanglement to measure things with mind-boggling precision. Imagine detecting minuscule magnetic fields in the brain for advanced diagnostics, gravity variations for mineral exploration, or tiny distortions in space-time. Quantum sensors could revolutionize medicine, geology, navigation, and fundamental physics research. The unfinished symphony, lingering quantum mysteries. For all its power and predictive brilliance, quantum mechanics leaves us with profound, unanswered questions, puzzles that poke at the very nature of reality. The tango continues. 1. The measurement problem. What really happens when we look? This is the big one. The mathematics of quantum mechanics describes two distinct processes. 1. The smooth, deterministic wave-like evolution of the wave function governed by Schrödinger's equation. 2. The sudden, random, particle-like collapsing of the wave function upon measurement, yielding a definite outcome. What is measurement? What triggers the switch from smooth wave to definite particle? Why does observation seem so special? The Copenhagen interpretation, the textbook view. Championed by Bohr and Heisenberg, it essentially says, don't ask what happens between measurements. Only the measurement outcomes are real. The wave function is not a physical wave, but a mathematical tool representing our knowledge and the potential outcomes. Measurement forces the system to choose one possibility, collapsing, say, probabilistically. The act of observation by a classical apparatus is fundamental. It draws a fuzzy line between the quantum system and the classical world of the observer. Critics find it vague about where that line is drawn and unsatisfying about the nature of collapse. The many worlds interpretation, the ultimate multiverse. Proposed by Hugh Everett. 3. It takes Schrödinger's equation absolutely seriously and says it always applies. Wave functions never collapse. Instead, every possible outcome of a quantum event actually happens, but in a different, newly branched parallel universe. When you measure Schrödinger's cat, the universe splits. In one branch, you open the box and find a live cat. In another branch, you open it and find a dead cat. Both realities exist, but you only experience one branch. It's elegant mathematically, no collapse postulate, but philosophically staggering, an infinite proliferation of universes for every quantum decision. And it doesn't explain why we experience only one branch. Decoherence, the environment matters. Not a full interpretation, but a crucial insight. It explains why we don't see superpositions in everyday life. Any quantum system is inevitably coupled to its vast, complex environment, air molecules, photons, etc. This interaction entangles the system with the environment, rapidly scrambling the delicate phase relationships of the superposition. The unique quantum coherence is lost to the environment, making the system appear to be in a definite classical state, like the cat being definitely alive or dead. Decoherence explains the effective collapse for all practical purposes, FAPP, without needing a special measurement rule, but some argue it still doesn't solve the fundamental problem of why only one outcome is perceived in our experience. Pilot wave theory, de Broglie-Bohm, postulates hidden variables guiding particles, with wave function as a real pilot wave. Relational quantum mechanics, Rovelli, says quantum states are only defined relationally between systems. There's no absolute state. Quantum Bayesianism, cubism, interprets probabilities as subjective degrees of belief. Each interpretation offers a different philosophical perspective on the math, but none provide a definitive, testable answer that everyone accepts. The mystery persists. What is the role of the observer? What is the true nature of the wave function? How does the definite world we perceive emerge from the fuzzy quantum substrate? Quantum gravity, unifying the cosmos and the quantum. We have two spectacularly successful physical theories. Quantum mechanics, QM, for the microscopic world of atoms and particles, and general relativity, GR, for gravity and the large-scale structure of the universe, space, time, black holes, the Big Bang. The problem? They are fundamentally incompatible. They speak different mathematical languages and make conflicting predictions in extreme regimes. QM treats space and time as a fixed, smooth stage on which particles act. GR says space and time are the dynamic actors, warping and curving in response to matter and energy. Trying to describe gravity using QM techniques, like quantizing the gravitational field, imagining gravitons, or trying to incorporate quantum uncertainty into the smooth fabric of GR spacetime, leads to mathematical nightmares, infinities that can't be renormalized, paradoxes. Black holes and the Big Bang singularity are realms where both theories are needed, but they refuse to work together. The quest. Finding a consistent theory of quantum gravity is arguably the biggest challenge in fundamental physics. Leading contenders include string theory. Proposes that fundamental particles aren't point-like, but tiny vibrating strings, or membranes. Different vibrations correspond to different particles. Crucially, it naturally includes gravity. A vibration mode is the graviton, and aims to unify all forces and particles. However, it requires extra dimensions of space, beyond our familiar three, lacks definitive experimental predictions so far, and exists in a vast landscape of possible solutions. Loop quantum gravity, LQG, focuses directly on quantizing space and time themselves. It proposes that space is not infinitely divisible, but made of tiny, discrete loops, or atoms of space. Time might also be granular. It provides a potential picture of the Big Bang without a singularity and insights into black hole entropy, but struggles to incorporate the other forces as seamlessly as string theory. Why it matters. Understanding the birth of the universe, the true nature of black holes, especially the information paradox. Does information swallowed by a black hole vanish, violating quantum principles? And the fundamental structure of space-time requires quantum gravity. It's the quest for the ultimate theory of everything. The third problem, the quantum physics, is the nature of reality. Is the moon there when nobody looks? Quantum mechanics challenges our deepest intuitions about an objective, observer-independent reality. Does an electron have a definite position before we measure it? Schrödinger's cat thought experiment highlights the absurdity of applying quantum superposition naively to large objects. The Copenhagen interpretation suggests properties aren't defined until measured. The many worlds view says all possibilities are equally real in different branches. Relational QM says properties only exist in relation to other systems. This leads to profound philosophical questions. Role of the observer. Is consciousness somehow fundamental to creating reality, a view most physicists reject? Or is it simply complex physical systems interacting? Decoherence. Where does the observer begin? Is a camera enough? A cat? A single atom? Non-locality entanglement. The spooky action at a distance confirmed by experiments suggests reality is deeply interconnected in a way that transcends space. Particles light years apart can instantaneously know the state of each other. This challenges the classical notion of local realism, that objects have definite properties locally, and influences travel no faster than light. A relational universe? Perhaps the universe isn't a collection of objects with intrinsic properties, but a network of relationships. Properties only manifest through interactions. The moon exists because photons bounce off it and interact with our eyes or instruments. Its moonness is defined relationally through those interactions. This relational view is deeply embedded in some interpretations of QM and resonates with some philosophical traditions. So, quantum mechanics is far more than the physics of the tiny. It's the foundation of our technological civilization, from the chip in your phone, to the laser in your Blu-ray player, to the image of your brain. It explains why the sky is blue and why gold doesn't rust. It's the language of chemistry and the key to nuclear energy. Yet, for all its power to describe how the universe works with incredible precision, it leaves us humbled before profound mysteries about what it is and why. The measurement problem questions the very act of knowing. The quest for quantum gravity seeks to unite the cosmic and the quantum. The nature of reality itself seems more elusive, more interconnected, and perhaps more participatory than we ever imagined from our classical vantage point. The quantum revolution rewrote the rules, gave us unimaginable power, and simultaneously deepened the mystery of existence. It tells us the universe is stranger, richer, and more bafflingly wonderful than our ancestors could have dreamed. The tango between the knowable and the mysterious continues, an endless, captivating dance at the heart of reality. And we, equipped with the tools quantum mechanics gave us, are still learning the steps. So, there you have it. The grand, predictable dance of classical physics, the world of balls, planets, and steam engines, and the bizarre, probabilistic, fuzzy tango of quantum physics. The world inside the atom, where particles are waves, cats are both alive and dead until you peek, and things separated by galaxies can be spookily connected. The difference isn't just scale, it's a difference in the very fabric of reality. Classical physics is the map we use to navigate our macroscopic world, a map drawn with the bold, clear lines of certainty and determinism. Quantum physics is the revelation that the paper that map is drawn on is made of something far stranger and more wonderful. A shimmering, probabilistic tapestry woven from uncertainty, duality, and interconnectedness. It tells us that the universe isn't just stranger than we imagine. It's stranger than we can imagine. Yet somehow, out of this fundamental quantum weirdness, the solidity of your coffee cup, the predictable arc of a basketball, the warmth of the sun, and the complex dance of life itself emerges. The quantum rules are the hidden choreography beneath the visible ballet. They power the device you might be listening to this on. They govern the light reaching your eyes. The next time you bounce a ball, appreciate its classical certainty. But remember, deep down, in the heart of every atom within it, a wild, unpredictable, and utterly fascinating quantum tango is swirling. That's the true magic of our universe, a constant, breathtaking interplay between the world we see and the profound, mysterious depths that make it all possible. The dance continues, and we're still learning the steps. Good night. Dream deep.